Have you ever been in this situation? You spend hours solving a problem, you write the code, it works perfectly for small inputs, you feel confident, you hit submit button, and then boom, time limit exceeded. Heart breaks, right? You check your code again, your logic is correct, your syntax is perfect, sab kuch sahi tha, everything was right. So why this is error? This is, my friend, is the coder's nightmare. But actually, it's just a puzzle waiting to be solved. The problem isn't your logic. The problem is your speed. Hello, everyone. My name is Supratim, and welcome back to Techmine Guru. Today on our DSA, the complete journey, we are going to learn the most critical skill for any developer. We are not just talking about maths today. Time complexity, we are going to decode, which is a secret language of speed. By the end of this video, that TLE error won't scare you anymore. You will understand कैसे बड़े inputs के लिए code optimize करते हैं. So grab your notebook, let's dive in. So today in this lecture, we are going to learn about time complexity, and the topics which are going to be covered are log basics, comparing iteration using graphs, time complexity with the big O notation, and why do we get TLE in online IDE. So let's start with the logarithm. What are logs? Log is the inverse of exponential function. So log of A on the base B means to what power we need to raise B such that we get A. So which means if B raised to the power C is equal to A, that means that C is equal to log of A on the base B. So let's see some easy examples. So what is log of 64 on the base 2? So when we raise 2 to the power 6, it gives us 64. So the log of 64 on the base 2 is equal to 6. In the similar fashion, log of 27 on the base 3 will be equal to 3, which means 3 raised to the power 3 comes to 27. That's why log of 27 on the base 3 is equal to 3. In the similar fashion, log of 25 on the base 5 is 2, which means that 5 raised to the power 2 will give you the result 25. So let's learn some powers of 2. So 2 power 1, 2, 2 power 2, 4. In the similar fashion, if we could see the powers of 2, it will be 2 to the power 10, which is 1024. Now, what if the value whose log is to be taken is not in the power of 2? How do we calculate that? So if log of 10 on the base 2 will come, which means when 2 is raised to the power 3, we get 8. And when 2 is raised to the power 4, we get 16. So there is a general rule in which we follow is that always take floor value in case of decimal number. So now one question arises that why we are considering the fact of 2 only. Because as we know, the computer science understands the language of binary, which is just 0 or 1. So we will talk every time about log. That means every time we are talking about log on the base of 2. So let's see some more examples. So there is one property of log which is called if log A to the power n is on the base A, that means it will be n only. So just we don't need to know all the log powers for this. Just this one property will be sufficient. Now, on the basis of the above principle, which we learned here, what is 2 to the power k? 2 to the power k if is equal to n, which means k is equal to log of n. In the similar fashion, log of 27 on the base 2 means we need to keep dividing 27 till it reaches 1. So how many times do we need to do the same? So 27 divided by 12, we will take the floor value, which is 13. Then 13 divided by 2, 6. 6 divided by 2, 3. 3 divided by 1, 2, 1. So how many steps are there? 1, 2, 3, and 4. So the answer would be 4. This is quite simple, right? Now let's take the example of n is equal to 70. So basically, we have to understand that there are two kinds of loops for which every time the log will be, the time complexity will come in log of n. So let's take one example. While I is equal to 1, I is equal to I by 2. So this is a simple loop where I is considered as n initially, and it is taking if I is greater than 1, You just do it half the loop. So in the first iteration, I will be equal to n. In the second iteration, I will be equal to n by 2. In the third iteration, I will be equal to n by 4. In the similar fashion, it will come as 1. This is exactly same which we are doing here to calculate log of 27 on the base 2. So n plus n by 2 plus n by 4 plus n by 8, which will come to 1. The harmonic progression of this series will result in log of n time complexity. Let's take one more example where on every iteration we are just doubling the loop. So when I is equal to 1, this iteration I is equal to 2. In the next iteration I is equal to 4. In the similar fashion, when I is equal to n, which is equal to 2 to the power k, right? Then k is equal to log of n. Again, the time complexity is similar, which is log of n. Now, let's take one more example. For I is equal to 0, I is less than n, I is equal to I into 2. Since I is starting from 0 and 0 multiplied by anything will be 0 only. So on every iteration, the I will be 0 only. So this loop will never end. So this is a kind of a classic infinite loop. Let's take one more example. Example 6. Suppose we have two loops for I equal which is running from for I is equal to 1 to n, second which is running from j equal to 1 to n. In this case, since both the loop is running from 1 to n separately, so here number of iterations will be n, here number of iterations will be n, right? Let's take one more example of a nested loop. Here I is running from 1 to n and j is running from 1 to n, but j is running inside I. So in the first iteration, when I is equal to 1, that time j will run till n iterations. In the similar fashion, when I equal to 2, j will run n times. In the similar fashion, when I equal to 3, j will run n times. When I is equal to n, that time also j will run n times. So how many times I is running? It will be n times into each iteration j is running for n iterations. So total will be n into n, which is n square time complexity. Let's take one more example. What if we take a for loop from running from 1 to n and a nested loop where j is equal to I and j is running from 1 to n and j is equal to j into 2. So in the previous examples, we have learned that what is the time complexity of this one, right? If you see my previous examples, it is the similar j, instead of I, there is j. So its time complexity is O of log of n, right? So in this also, the inner loop will give you that it is log of n, and the outer loop is running how many times? 1 to n. So if you find it difficult to understand, so let's make a table for this. When I is equal to 1, what will be the j? 1, 2, 4, 8, n till n. That means log n iterations, right? In the similar fashion, when I is equal to 2, j will again run from 1, 2, 4, 8 and n, which means again log n iterations. In the similar fashion, till we reach n, the inner j loop will always be log n. So the total time complexity will be n multiplied by log n. Let's take one more example. I is running from 1 to 4, j is running from I to 1, 1 to I. So this is not O(n) square. This is n only. How? Because since I is running from 1 to 4, not from n, I has been fixed that it can run from 1 to 4. So when I is equal to 1, j will run from 1 to 1, which means 1 iterations. When I is equal to 2, j will run from 1 to 2, which means 2 iterations. When I is equal to 3, j will run from 1 to 3, 3 iterations. When I is equal to 4, j will run from 1 to 4, 4 iterations. I hope the range, if we are given range, we can easily calculate the iterations, right? Because in the last class, we learned that if the range is from A to B, close bracket, which means the formula is B minus A plus 1 is the total number of iterations we have to calculate. So here B will be 1, A will be 1, then B minus A plus 1 is equal to 1. In the similar fashion, B is 2 minus 1 plus 1. What it will be? 2 iterations. So we are calculate calculating on the basis of the same. Let's take one more example. What if I is running from 1 to n and j is running from 1 to I? So how to calculate iteration? When I is equal to 1, j is will be equal to 1. When I is equal to 2, j will run from 1 and 2. When I is equal to 3, j will run from 1 to 3. So total iterations will be 1 plus 2 plus 3 up to n. So in the last class, we learned that if the sum of the series is 1 plus 2 plus 3 plus up to n, then we have n into n plus 1 by 2 as total number of iterations. So just keep the total number of iterations and it will tell you the big O complexity. But here one question arises that if you extract out this one, it will come somewhere around n square by 2 plus n by 2, right? Whereas this constant term 1 by 2, and where are this the lower order terms n by 2. So we will learn about this further. Let's take one more example as when I is equal to 1 to n, j is equal to 1 to 2 to the power I, right? So this is a difficult thing to calculate. So let's calculate via this table. So when I is equal to 1, j will be running from 1 to 2. When I is equal to 2, j will run from 1 to 2 to the power 2 to the power I it was. So it's 2 square. In the similar fashion, when I is equal to n, j will run from 1 to 2 to the power n. So when j is running from 1 to 2, how many iterations it will be? 2 iterations. When j is running from 1 to 4, how many iterations it will be? 4 minus 1 plus 1. It will be again 4 iterations. In the similar fashion, when I is running from 1 to 2 to the power n, it will be 2 to the power n iteration. So what will be the total number of iteration? 2 plus 4 plus 8 up to 2 to the power n, which is sum of GP, which we learned in the previous class. So when 2 to the power 1 plus 2 to the power 2, we are calculating all the iterations, we are summing up all the iterations, we will get 2 into 2 to the power n minus 1 divided by 2 minus 1 by keeping in this formula of a into r to the power n minus 1 divided by r minus 1. So this gives us that this is 2 into 2 to the power n minus 1. So the total time complexity will be not this one, O of 2 to the power n, right? Now let's compare iterations of two algorithms. So let's take one algo as 100 into log of n and another algo as n by 10. Let's take an example to understand this algo. Let's take n is equal to 8. So algo 1 will give 100 into log of 8 on the base 2, which is 3. 100 into 3 is 300. And algo 2 is 8 by 10, which is 0.8. So you must be thinking that algo 2 is far better than algo 1. But this is not correct. This you are seeing for smaller input. So when input size is more than 3900, algo 2 is far better than algo 1. And why this happens? So log n will be going like this and O of n will be going like this. For the initial sum input, you will feel that algo 2 is better. But as you go further, you will feel that algo 1 is better. So how to calculate big O? Because you know till now that we know how to calculate the number of iterations. So from the number of iteration, we were calculating time complexity, right? So there are some basic steps to calculate big O. First step, calculate iteration based on input size, which we have done earlier. Now we have to ignore lower order terms and ignore the constant coefficient. Suppose our algo 1 gives that it is 100 into log of n, then big O will be O of log of n. So where we are ignoring the constant coefficient. In the similar fashion, in algo 2, n by 10, the constant coefficient is 1 by 10. So we need to ignore that and the big O notation will be O of n. So let's take one more example, 4n square plus 3n plus 1. So in this, we need to ignore the lower order terms, which is 3n plus 1. And then we need to ignore the constant coefficient of this n square, which is 4. So now big O complexity is On square. So we will also learn that why we are ignoring the lower order terms and why we are ignoring the constant coefficient. So before that, let's try to memorize this complexity order from smallest to largest. It seems a bit difficult to remember to memorize, right? But there's a trick into it. So the trick is you just have to remember this much, that log n is always smaller than root n. Now, in this similar, log n is always smaller than root n, is what you know, right? Then you start multiplying on all the on each term by root n. So if you multiply root n here, what it will be? Root n log n. If you multiply root n here, it will be root n into root n, it will be n, which means root n log n is lesser than log n, is lesser than n. In the similar fashion, if you again multiply by root n on this one, you will get n log n, and in this one, if you multiply root n, it will be n root n. And after that, everything is simple, right? N root n means n power 3 by 2, which is always smaller than n by 2, n square, which is again smaller than n cube, which is again smaller than 2 to the power n, which is again smaller than n factorial, and which is again smaller than n root n. So you just have to memorize these two. Everything else will be easier for you to understand. So let's take one example. Let's take an example of 36. So 1, let's write corresponding value of everything on the basis of taking n as 36. So log of 36, which will come somewhere around 2 to the power 5 is 32, which will come 5. Root 36 will be 6, which is again greater than 5. Then root n log n means 5, root n is 6, and log n is 5, which is lesser than 30, which is equal to 30, which is again smaller than n, right? 36, n is 36, and log n is 5, which is 36 into 5 is smaller than 36 into root of 36, which is 36 into 6, which is again clear. 36 into 5 is lesser than 36 into 6, which is lesser than 36 into 36, which is lesser than 36 into 36 into 36, which is lesser than 2 to the power 36. Why? Because we learned that 2 to the power 10 was somewhere around 1024, right? So 2 to the power 10 is 1024, then 2 to the power 30 will be 1024 into 1024 into 1024, which is a very big number, right? In the similar fashion, 2 to the power 36 is lesser than 36 factorial, which means 36 into 35 into 34 till we reach 1, which is a very large number, which is again smaller than 36 to the power 36. So with this example, we can understand that this ordering is correct. And to memorize this ordering, we need to just remember that log n is smaller than root n. That's it. So let's come back to this example again. Suppose your iteration comes around 4n square plus 2n plus 100 log n plus 1. You need to ignore the constant coefficient, which is 4, and you need to ignore the lower order terms, which is 2n plus log n plus 1. Since we know that n square is greater than n also and log n also, right? So what is the time complexity of this? So the time complexity will be O(n) square. So now let's understand why we are ignoring lower order terms. Suppose, so if you see the n square log n and 10n is our time complexity, then n square log n will be the original contributor, higher contributor, right? That's why we are ignoring the lower order contribution. So to understand this better, we can also think in a way that what is the percentage of contribution which lower order term is doing. So when n was equal to 10, at that time lower order were giving value of 100, which means 100 divided by 1000, which is 10%. When n is equal to 100, that time lower order value was giving 1000 and higher order value was giving 10 lakh, which was approximately 0.1% contribution. In the similar fashion for n equal to 3 as well. So from this we understood that for larger input, contribution of lower order terms, for larger input, contribution of lower order terms is almost negligible. So now we also need to understand why we are ignoring constant coefficient. Suppose there are two algo, algo 1, 10 log n, and algo 2, n. What do you think which will be the winner from both the two algos for larger input. We already learned above, right? That if n is very, very bigger, that time log n will be very smaller and n will be higher. Take the example of 10,000. So log of 10,000 will somewhere come around 100 to 105, something like that. Okay, 105 into 10, which will be 1050. And in this, since n was equal to 10,000, the algo 2 will give 10,000. So what do you think? Which is the bigger, which is the winner algo? This one, right? In the similar fashion, 100 log n and n, two algos are there. Which one will be better? Still 100 log n will be better. In the similar fashion, n square, both are same. So any algo will be better. Now in the next algo, 1000n and n square by 10. In this case also, for higher input, algo 1 will be much faster than algo 2. So if you see, the constant coefficient which is there in each algo is not making any contribution. So we can ignore the constant coefficient. But there are some issues with the BIGO as well. So let's see what are the issues in the BIGO. In BIGO, we can't say that one algo is always better than another algo. So let's take one example. What if algo 1 is 10 to the power 5 into n and algo 2 is n square divided by 10 to the power 5. So in this case, algo 1 is telling that its BIGO complexity is O of n, and algo 2 is telling that its BIGO complexity is O n square. Algo 1 is better than algo 2 only for very large input. So there is always an issue with the BIGO regarding this kind of scenarios when constant coefficients are very higher. Also, if two algos have same higher order terms, BIGO is not capable to identify which one is the better algo. Suppose algo 1 is n by 2, which gives us BIGO as O of n, and algo 2 is n. We are saying that algo 1 is always better than algo 2, but BIGO says they are same, right? Now let's understand why in online IDEs, why we get TLEs. So all the online IDEs have the processing speed of their servers as 1 gigahertz, which means 10 to the power 9 instructions per second. And TLE comes every time if our code runs for more than 1 second. So let's take an example on this. For I is equal to 0 to I is equal less than n, I plus plus, s is equal to s plus I. What do you think? What will be the number of instruction in this case? So this will be 1 instruction, this will be n instruction, this will be n, and this will be n. So total number of instructions will be 1 plus 3n instructions. So if one iteration is taking 10 instructions, then 10 to the power 9 iterations will take 10 to the power 9 instructions will take around 10 to the power 8 iterations, which will be in 1 second. So one iteration, so suppose if one iteration is 100 instructions, then 10 to the power 9 divided by 100, which means 10 to the power 7 iterations are possible in 1 second. So we have to start thinking that what can help me in that case, which time complexity can help me in that case. So in this kind of scenarios, we cannot go for O(n) square, O(n) cube kind of complexity. So there we have to start thinking that how on each step we can reduce our number of instructions, or we can double our processing the instructions, so that we can come up to something like O of n log n or something like that. So today you didn't just memorize some bookish rules, you built intuition. You now know that efficiency is all about scale. You now know how to calculate BIGO correctly. And most importantly, you know its blind spot and how to use it to avoid that nasty TLE error forever. Earlier, you were just writing code. Now you understand the cost of every line you write. You are no longer just using BIGO. You understand it, and that's a massive difference. But remember, this is just the beginning. The journey continues. In the next video, we are going deeper. We will master space complexity and finally dive into our very first core data structure, arrays. Trust me, you don't want to miss that. If this video helped you clear your concepts, hit that like button. It tells me that I'm able to help you or not to grow. And if you haven't already, subscribe to Techmine Guru right now. Don't just stop, just keep learning. Stay on the path. Your complete journey awaits. See you in the next class. Signing off. Keep coding, keep optimizing, keep learning.